All right, we're going to finish up with number 9. Number 9 is pretty interesting. Number 9 is going to require you guys to have some critical thinking skills here. Now, I'm going to run through this, so it's not like you have to come, pull it out of the ether here, but you do need to remember this type of thought process. Copper's electron configuration might be predicted to be 3d9 4s2. Okay, and you guys would predict that that is as well. If you guys, some of you remember that I actually tricked some of you during one of the journal writes, and I had you write the electron configuration of one of these elements that is an exception. And I saw that most of you went to the back of the book and copied the electron configuration out of that periodic table. Well, that's how I knew you were simply copying these electron configurations and not doing them yourselves. If you were to do them yourself, you would predict that it was 3d9 4s2. But in fact, like we talked about that particular day, its configuration is 3d10 4s1. All right, it means that we seem to have stepped away from the off-bow principle, and we're filling the 3d10 suborbital before we fill the 4s1, even though the 3d is slightly higher in energy. The two elements below copper in group 11 behave similarly. And if you want to double check this, feel free to look at your periodic table. But we want to think about this idea, and we have a few questions to answer. Which configuration for copper is apparently more stable? The one that you predicted, or the one that it is in real life? And that's not a trick question. You need to go with the electron configuration that you see in real life. Because one thing that we see in science, in the natural sciences, is that nature favors low energy states. Nature favors stability in every setting. In every setting, it favors stability. And so when you see nature doing something that you don't expect, for some reason that apparently you don't know about, which is fine, that you don't know about, that's more stable. And as a scientist, it's your job to figure out what about that situation makes it more stable. And once you do that, you figured out something about the world that you can add to the general breadth of science. So this is what we see in nature, and so this, by definition, is going to be the actually more stable one. Now, the reason being, once you get to these levels of 4s and the 3d, at that point, these suborbitals are so similar in energy that the energy difference is actually so little that when you get to this 3d9, it's more energetically favorable to fill the 3d suborbital completely and have that completely filled, as opposed to having the 4s2 completely filled. You guys don't have to be able to do the math on that. It's just an exception that you want to be aware of. So B, is the d suborbital completed in the atoms of these three elements, meaning copper, and then the two elements below copper in group 11. So is the d suborbital completed in these atoms? Well, we're seeing 3d10, right? We just said that apparently the most stable version is 3d10 for copper, and so yeah, that d orbital right there is full. So yes, yeah, that's what's resulting in that elevated stability. And then C, every element in period 4 has 4 levels of electrons established. True or false? True or false? Well, we're looking at the 4th period. This might sound like a weird question, but let's try to think it through here. Every element in period 4, okay, so that's right here and all the way across, has 4 levels of electrons. 4 levels of electrons. What could we possibly mean by 4 levels of electrons? Do we mean we're talking about the 4 blocks, right? 4 different sublevels. You have S block, D block, P block, F block. Do we have that? Well, that can't be what we're talking about. Because those aren't levels. Those are simply orbitals and different shapes of orbitals. The only time we use the word level in chemistry is when we're talking about energy level. And what do we associate with energy level here? principal quantum numbers. These different periods. And so if the question is telling us elements in period 4, right? So, potassium, calcium, let's pick a random one over here, iron, okay? Iron. Does iron have 4 levels of electrons established? Well, if you look at the kernel electrons, it's got your 1s, okay? So that's n equals 1. It has the n equals 2 because it's got all these kernel electrons as well. It's got n equals 3. And guess what? The reason it's in period 4 is because it has some electrons from period 4. And so, yes, in order to be in period 4 and have those electrons, you must have 4 levels of electrons established. Now, the question doesn't say for full levels, right? For full levels. Potassium right there doesn't have a full 4th period, but it does have an electron in the 4th period, okay, in n equals 4. It has at least 1. And so that's what we get out of this word established right here. Yeah, we have 4 levels of electrons established. Doesn't mean that they're complete or full. This means that they are in existence. So I'm going to go with